Okay, now sharing is working. Can everyone hear me? Also, where did my chat go?
Yes.
Awesome. Sweet. Chat set up. We are talking about sections 4.1, 4.2, and is it 4.3? Sorry. I wrote this down and then promptly lost it. We were talking. Yeah. Good morning. Thank you guys, by the way, so much for coming, even though it's not at the usual time. I'm so sorry about that. The internet was just not functional yesterday, and it's kind of hard to hold these sessions without internet. So, right. We are looking at max-min inflection points, right? Right. Okay. I'm on the right track. Okay. So, basically, these sections are us kind of setting up and beginning to, like, essentially use all of this work that we've put into finding derivatives. Sorry, I'm checking to make sure that we're recording. Yep, we're good. So yes, so we're basically like organizing this in a way that we're going to be able to use some of the concepts of what a derivative is. Why don't we start by looking at some graphs from 4.1, or at least my 4.1. Again, still don't have the right book. And analyzing the critical points. So let's look at problem 2, where we have a function that looks like, I'm using green. Something that looks like this. And this is the function f of x. So it would like you to identify or indicate all of the critical points. How many are there? And identify them as a maximum, a minimum, or neither. So, where are our critical points? Starting from the left and kind of working our way over. You can kind of just, if you guys can see my pen, right? You can just stop me whenever.
Yes.
We hit a critical point. Yep. And what type of critical point is that?
Maximum.
And then we keep going. Yes. So the slope of the tangent line is 0 at a critical point. Any other critical points in this graph?
Another min and another max.
Yep. So here we have another max, and here we have a min. And at all of these points, the slope of the tangent line, if I were to draw it, would be 0. So here's my tangent line. You can see that it's flat. The slope is pretty much 0. And that's kind of how it is situated. So let's think about you guys are comfortable with the concept of like mins, maxes, critical points? Like, would you like to do algebra instead of graphing? I think that might be helpful. A lot of the times, the way that these problems tend to be set up is that they will give you a function, and then they will like go through and like ask you for, You know, what are the critical points? Is it a min or a max? What are the inflection points? Where is it concave up, concave down? And then at the end, they will have you graph the function based upon what information you have. So that's kind of how the problems tend to be set up. So you start more with the algebra of it than you do with the graph. So let's start with problem 16. Where we have the function f of x is equal to 3x to the fourth minus 4x cubed plus 6. So here's our function f of x. We need to find all of the critical points and then use the first derivative test to determine if they're maxes or mins. Where should I start? What's the first thing that I should do? Yes, I'm going to find the derivative. So the derivative of this is going to be 3 times 4, that'll be 12x cubed using the power rule minus 12x squared using the power rule plus 0. So here is my derivative. Now what do I do? I have the derivative. Equals 0. So the derivative is going to be equal to 0. What I'm going to do is I'm just going to add plus 12x to both x squared. So I'm going to end up with 12x cubed is equal to 12x squared. I'm going to divide it by 12x squared. So I end up with 12's cancel out here, x squareds cancel out, 12's cancel out. Here, x squared is going to knock off 2 of those x's. So we're going to end up with x is equal to 1. So what does that tell us? What does x equal to 1 mean? Tells us where, yeah, exactly. Tells us where the critical point is. Sorry. So we now know where the critical point is. How are we going to determine whether or not it is a max or a min? How am I going to set up? Yes. So the way I'm going to do this is I'm going to set up the line. I'm going to say this is x is equal to 1. This is x at that point. Sorry. X equal to 1 right here. And then the way that I set this up is I kind of go in here and I'll say that this is -1 and I'll say that this is 10. So those are numbers that are definitely not 1. And then I'll go through and I'll say this is 12 times -1 minus 12. So that'll be -24. And that is going to be a negative number. All I care about is the sign. And then over here with 10, that'll be 12 times 10 cubed, which is going to be 1,000 minus 12 times 10 squared. So that'll be 12 times 100. So is that going to be positive or negative? 12,000 is going to be larger than 1,200. So 12,000 minus 1,200 is positive. Yep. So what's happening here? What am I looking at? Local min. Yep. I'm thinking that I'm missing something actually. Because if I say that x is equal to 0, then I should also have a my derivative is equal to 0. So I'm going to go through and plug that in. Sorry I missed that. So here we have 1, here we have 0, and then here I'm going to have a half. So f prime of 1/2 is going to be 12 times 1 over 8 minus 12 times 1 over 4. So 1 over 4 is 12 times 1 over 4 is going to be 3, and that is 6 over 4, 3 over 2. So that is 1.5 minus 3. So that is going to be negative. Okay. So now what am I looking at here? I've got 2 critical points now. Again, sorry. Here they are. We have a local min, yep, right at x is equal to 1. And we don't have a min or a max. This is a neither situation. But it is a critical point. Okay. Let's also go ahead and do number 19. When we have the function f of x, basically the way that this works is that you have a max where you're going from your function is increasing and then it begins to decrease. You have a min where your function is decreasing and then it begins to increase. And you can kind of see that we have a min shape here and we have a max shape here. And then we have neither situations where we're decreasing and decreasing or increasing and increasing. And these are saddle points. So this will look like something like that, and this will look something like this. And essentially there's just, the slope is equal to 0, but there is no set max or min because it continues to increase or decrease after the point. Does that make sense? More or less? Yep. Nope, it is a critical point because at this point the slope is equal to 0, but it's not a min or a max. Yes. So critical point does not mean it is either a min or a max. It means it can be, which is why we do this first derivative line test to make sure that it is. And the local minimum is that x is equal to 1. Yep. Awesome. Okay. At 19, we have f of x is equal to x over x squared plus 1. Our first step is going to be to take the derivative of this. How am I going to take this derivative? Yes. So we'll say that I'm going to call it h of x, just because I want to keep my language straight, is going to be equal to x. H prime is going to be equal to 1. And then over here, I'm going to have g of x is equal to x squared plus 1. and g prime of x is going to be equal to 2x. And then I need to put them all together in the form h prime times g minus g prime times h over g squared. And this is the quotient. So I'm going to end up with f prime of x is going to be equal to 1 times g, which is going to be x squared plus 1 minus 2x times x over x squared plus 1 squared. So this is going to get simplified into x squared plus 1 minus 3x squared over x squared plus 1 squared. Or minus 2x squared plus 1 over x squared plus 1 squared. Okay, are we good with using the quotient rule in this way? We've got our derivative now. We're looking for critical points. When f prime of x is equal to 0, like what essentially here should I set to 0? What is equal to 0 if f prime of x is equal to 0?
Is that negative 2x squared plus 1?
Yep. Sorry, there's a weird little gap there. So basically, this whole fraction is equal to 0 if the numerator is equal to 0, right? Because if I have 0 over like 4, I'm going to end up with 0. So I'm going to end up setting the numerator equal to 0.
Liv, can you please check my notes?
Yes, you're right. Sorry, I guess I'm out of it today. I'm so sorry. Keep making all of these algebra mistakes. It is 2x squared. So this is minus x squared, because we still do have x squared minus 2x squared. I just pulled that 3 somewhere it shouldn't have been, I guess. But you're right. So we're going to set the numerator equal to 0. So that we can find out what the numerator has to be, or what x has to be to set the numerator equal to 0, and that's the whole thing equals 0. This is going to end up being x squared is equal to 1. So x is equal to plus or minus 1. What am I missing here? What is something important that we need to make a note of? I need to check my denominator. And in this case, it's not going to be able to equal 0 because we're going to end up with something that's imaginary, but I still do want to check it so that I don't accidentally set something that is basically a point that doesn't exist. So I'm checking it, and I know that x squared is equal to minus 1. That's going to be really hard. We're going to end up with an imaginary number because we can't take the square root of a negative number. So this isn't going to impact our domain, but I do just want to make sure that we check the denominator here. Okay, so our critical points are x is equal to plus or minus 1. We've established that both of those points can exist in this function. Let's use our number line. Here we have -1, and here we have +1. Here I'm going to have I'll use -2, 0, and -2. So for -2, this is going to be 4 squared. So -4 plus 1, so it's going to be basically how I do this. Sorry, I'll practice it like this. Is I say I have a positive number, say this is positive divided by a positive number, I know it's going to be positive. Negative divided by negative, positive. Negative divided by positive, that'll be negative. So I kind of just bracket it by signs. Here I know I'm going to have a negative number divided by
touches in consecutive games, but his touches have gone up each of the last couple of weeks. Like there is a Carlos Hyde resurgence, and what's clear to me here, more importantly than anything else, is that Bill O'Brien and his staff believe in this kid. They have a very simple set of instructions for Carlos Hyde.
Okay. Right. So we have a negative number on top divided by a positive number on bottom, so that's going to be negative. Then over here, it's going to be 0, so that's going to be 0 plus 1, so it'll be positive divided by a positive number, so it'll be positive. The reason I'm drawing these arrows in the way that I do, down and up, is basically so that I can better visualize it. I could just have a negative sign or a positive sign, but for me, the arrows make it a lot easier to visualize. And then over here at 2, I'm going to end up with -4 plus 1, so it'll be a negative divided by a positive again. So it'll be negative. So, what do I have here? At x is equal to -1, yes, both are critical points. That is given by this step right here. Yes, I have a local max at 1. And at -1, I have a local min. Exactly. So we get the fact that the critical points from this, setting this equal to 0, and then we get the fact that there are a local min here at x is equal to -1 based on our line, and then a local max at x is equal to 1 also based on our line. Okay. We have a lot of material to move through. I think we have 4 sections worth of material. So I'm going to start moving into 4.2, which is, again, it's a very similar concept. Basically here, in 4.2, where we're talking about inflection points, which I hope is the same section that you have. If it's not, I'm sorry. I will instead call this inflection points. We're basically going to do the same type of thing. I'm going to draw the same graph that we had before, where we have something that looks like this. And now tell me about where the inflection points are. So we said we had maxes and mins over here. Yes, so these points are going to be between the maxes and the mins. Here I have an inflection point, and here I have an inflection point. What does an inflection point mean? Yes, it means that I'm going to be switching from positive to negative second derivative, or from a negative to a positive. How does that correspond in this graph? What am I looking at in this graph? I'm going to be looking at concavity. When we think second derivatives, we think concavity. Here is concave up. Up. And here, the graph is concave down. And the point at which it transitions from being concave down to concave up is at this inflection point. So, given all of that, let's try to do some algebraic determinations of what we've got going on here. Okay, let's start with, let's do number 14, which for me looks like this. So, we need to find the critical points and find the inflection points. Step 1, what do I do?
First derivative.
Yep, first derivative. Using the power rule, I'm going to end up with 6x squared plus 6x minus 36. We can go ahead and use this to find the critical points, or step 2, I'm just going to go ahead while I'm on the roll, find the second derivative, which is going to be 12x plus 6. Here will be my critical points work. I'm going to say that 6x squared plus 6x minus 36 is equal to 0. I'm going to factor out a 6 because I don't really want to deal with that right now. So, how can I factor this? It's a quadratic equation. I can factor it into x plus something, x minus something times x plus something. X plus 3x minus 3. Let's check this. This will be x squared plus 3x minus 3x minus 9. So this will be x squared minus 9, which is not what we have up here. Really close. Yep, exactly. No, you're good. That's why we double check. So now we have x squared plus 3x minus 2x minus 6. So this will be plus x minus 6. And that's what we have. So, perfect. What does this tell us? Where are my critical points? This whole equation is equal to 0 when any one of these pieces equals 0. So when 6 is equal to 0, when x plus 3 is equal to 0, or when x is equal to minus 3, and x is equal to 2. These are our critical points. Then I'm going to set up the line Over here, here is -3, here is 2. I'm going to go ahead and say that this is -5, 0, and 5. And the great thing about this is that you can go ahead and immediately see what this is. So this is a positive number times at -5. -5 plus 3 is a negative number. Positive times a negative times a negative. So that'll be a positive number. Negative, negative, negative times a negative is a positive number. At 0, this is going to be positive times negative. So it'll be a negative number. And at 5, this is going to be positive times positive times positive. So it will be, again, a positive number. And we're going to end up with, here we have a local. This is a max or a min at x is equal to -3. Max. And then at x is equal to 2, we have a min. Awesome. Okay, so that was our first derivative stuff. Next, we need to do our second derivative stuff.
Could I
What
ask
does it
a
mean?
quick question?
Oh, yeah, for sure.
It's really dumb. Are we supposed to know if this is above the x-axis or below the x-axis and what the y values are for the critical points?
How would you find the y value for a critical point?
I have no idea.
I promise you, you definitely do. It's just we've been doing so much junk with this derivative that it's basic. If I have an x value and I need to find a y value.
Oh.
Yep. X is equal to -3. I just go ahead and plug -3 in wherever there's an x.
I totally missed that. Thank you.
Yep, no, you're good. So that is how we would go about finding a y value for any of these points. And that's how you can check. If you really want to go back and check, like if my local max is bigger than the points around it, I could check -3, -5, and 0, and it should come out that way in the original equation. Okay. For the second derivative, what does it mean to be an inflection point? Yep, we're checking concavity. We can find the inflection point by finding when the second derivative is equal to 0, exactly. So I'm going to set this equal to 0. And I can go ahead and factor out a 6 again, and I'll end up with 2x plus 1 is equal to 0. So this is equal to 0 when 2x plus 1 equals 0, which is going to be when 2x is equal to -1, or when x is equal to -1/2. So here is when x, that is equal to 0 when x is equal to -1/2. And that makes sense. -1/2 times 2 is -1, plus 1 is 0. That's where my inflection point is. Can we determine, do we know a way to determine if it is concave, if this is a change from concave up to concave down, or from concave down to concave up? The sign, yes. We're going to do essentially the exact same thing we did. The sign of what? What sign? Yes. Yes, exactly. Okay. Sorry, I just wanted to make sure everyone was on the right track. So here we'll have minus 1/2. And here we'll go ahead and put it in as -1, and here can be 0. So here we'll have a positive 6 times -2 plus 1, so negative. So that's going to be negative. And here we'll have 6 times 0 plus 1, which is going to be positive. So a negative second derivative means what? Concave down, and we're moving to concave up. Everything makes sense? Does this make sense? Like, in terms of the critical points and everything? If I were to sketch this out, which I can do at this point, I'm going to do it not in that mint green, but I could go ahead and find out what my y values are, and I am able to go ahead and say that I have something that looks like, I'm not going to go ahead and find the y values. I can, but I'm not going to right now, just for the sake of time. I just want to make sure that we can see that I have a, here is -3, I have a max here, here is 2, I have a min here, and here at -1/2, I have the inflection point. So you can kind of see the shape is such that I have concave down before, and then after I have concave up. So here's my concave down, here's my concave up, which makes sense because I have a maximum over here and a minimum over here. Again, these points are not exactly where it is. This whole thing could just be above the x-axis, but that's basically like the shape that I'm looking at. Okay. Any questions? Let's do a couple global max and min problems. The idea with the global max and min is basically that we're looking for something that is just objectively the largest point, the largest y value on any graph. And I think a good problem to do that really like brings a lot of this together is problems in my book. It's 16 through 19 in 4.3, where you need to find both first and second derivatives. You need to find the critical points. You need to find the inflection points. You need to evaluate f at its critical points and at the end points of the interval to determine the local and global max and min, and then you need to graph it. So let's do one of those. Let's do, would you guys like to do a sine function? Or would you guys like to steer away from a periodic function? Like, are you comfortable enough with this material that we can jump into a periodic?
Yeah, I'm assuming something like that would be on a test in the final.
It would be, yes. It's just kind of as we learned last week, if we jump into too hard of a problem too fast, we can get lost pretty quickly. So I didn't want to do that. But if you guys are up to it, then we're going to do f of x is equal to x plus sine x. On the interval, 0 is less than or equal to x, which is less than or equal to 2 pi. So, step 1, we need to find the first and second derivatives. What is the first derivative? Yep. Looking at 1 plus cos x. And then over here, we'll have our second derivative, which is what? Perfect. Okay. All right. So for our critical points, we have f prime of x is equal to 1 plus cos x, which for critical point, we want to be equal to 0. That means that we want cos x to be equal to -1. When is the cosine of x equal to -1? I'm going to sketch out a quick cosine curve. A cosine curve kind of goes from like here to over here. And it is equal to -1 right here. This is just the entire curve. I'm trying to find out what x value cos of x is equal to -1 at, right? Okay. If this is 2 pi, are you familiar with how a cosine curve looks? Okay. So this point here is where it equals -1. Do you know what this x value is right here? It's just going to be 2 pi. This is a standard regular old cosine. Is that 1, or is it, we kind of measure the x-axis in terms of pi, right? So we can do this based on the cosine graph, or we can do this based on the unit circle. And I definitely prefer doing this based on the cosine graph because I really struggle with the unit circle sometimes. And the unit circle can get turned into like a whole thing. But what I want to make clear is that this is pi. Like I'll have a graph that looks like this. And this is a cosine graph. And this is x is equal to pi over 2. This is pi. This is 3 pi over 2. And this is 2 pi. So these are all of the major points along the cosine curve. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So cos of pi is equal to -1. Are you following, or not so much? Basically what I did was I took a graph and I reversed it because I knew what I wanted my y to be. I just needed to use it to find out what x was at that point. I think it's handy. You can also, like I said, use the unit circle to do this. This is the way that I find the easiest because I have these memorized.
Is the period, it's always 2 pi over b, right?
Yes. In this case, b is going to be 1 because there's no b in the equation because we're only looking at, like, if there was a b in the equation, if this was like 1/2 x, then the period would be changed. But because it's just cos x, it's not. So the period is 2 pi.
Okay.
So basically what I'm saying here is when cos x is equal to -1, x is equal to pi, plus or minus 2 pi, because it's a cosine graph. But we're looking at our range, and the only time in this range where cosine of x is equal to -1, this is the graph essentially of cos x at this time. The only time in this graph where cos x is equal to -1 is here at pi. So x is equal to pi. Are happy with this, because we're kind of like building a lot on foundations that we're setting right now.
So if it's cosine x, it's always equal to -1.
Yes, what we're saying here, like our train of logic is f prime of x is equal to 1 plus cos x. We want f prime to be equal to 0. So 1 plus cos x is equal to 0. Then, if that's true, then cos x must be equal to -1. What is x when cos x is equal to -1? X is pi. That was our train of logic.
Okay.
You don't sound too pleased with that. Is that just like a processing thing, or is there something?
It's just I understand the sine and the cosine and the graphs. I'm just having a hard time when I see the cosines and what cosine or sine and what it's supposed to equal in situations like this.
Yeah, this is really hard. That's why I like to have this memorized in case it's something really easy. Another thing, you might just want to focus on unit circle, because if you end up with something like √3/2, that's something I think you can find with the unit circle. Like, I think that's cos of pi/6. So if it's cos x is equal to that, then I think x is equal to pi/6. I would have to check again because I don't have those memorized like I should, but knowing those trig functions is going to make this transition a lot easier. So if we can get past right now, like, you're okay with the concept of what we're doing, like the core of how we're getting x is equal to pi. It's just a matter of memorizing cos of pi is equal to -1.
Yeah, I'm good with that so far.
Okay. Then if you don't mind, we're gonna like try to like find the rest of we have the critical point now. Here's our one critical point within our system. This is our critical point. We need to know the actual whole point. How do we find the like coordinate point here? I need this in an x, y form. If x is equal to pi, what is y equal to in my original function?
-1?
original function. This is what we were talking about earlier when you said if I have x of pi and I need to find out what it is as a coordinate point in the original function, I say this is f of pi, which is equal to pi plus sine pi. Yeah? So I'm going to end up with the point pi pi. Because sine of pi is going to be equal to 0. Thoughts? Okay. Next, we're going to determine if this is a min or a max. I'm going to set up my line. Here, I'm going to have pi. Here, I'm going to say, I'm going to have, I don't know, I'll call it 0. No, I'm not going to call it 0. Yes, I'm going to call it 0. And then I'm going to have pi over 2 and 3 pi over 2. Let's not make things too complicated. I'm going to be using this equation up here. And I'm going to say this is 1 plus cos of pi over 2. Right? Cos pi over 2 is going to be 0. So this is going to be 1 plus 0, and it's going to be a positive number. Maybe this was a mistake. And then I was going to say over here, I have 3 pi over 2. I wonder if this is not a good call. Let me try something else. I'm trying to figure out what's going on here. Let's try 0 and 2 pi. Okay. It's going to do the exact same thing. I guess that means it's not a min or a max. Basically, what's going on here is that if I have 1 plus the cosine of 0, I get 2, which is a positive number. And then if I have 1 plus the cosine of 2 pi, I get 2, which is a positive number. So this is neither. Functions tend to be wonky. I assumed it was going to be a local min or a max, but I must be wrong because it's not showing up like that. Okay. So there we are with our crit point stuff. We found our critical point. We found the ordered pair for a critical point. We found out that it was neither a local minimum or a local maximum. Now we're going to go and do our inflection point stuff. We have negative sine x. When is negative sine x equal to 0? Anyone know when sine of x is equal to 0? Zero, yes. Any other points? pi. What is, I guess you're right, yeah. Should look like, just thinking. So this is negative sine x. Right? And there are 3 points where it is equal to 0. Here at 0, here at pi, and here at 2 pi. And all 3 of those points are within our range, or domain, rather. So those are our 3 inflection points. Then we're going to set this up so we have 0, pi, and 2 pi. I'm going to draw that graph again because I probably shouldn't have taken it down. Here's 2 pi, here's pi, and here's 0. So here's pi over 2. Here is 3 pi over 2. And we extend like this. Here's negative pi over 2. And the reason I'm drawing that all out in that way is because I'm going to put all of those numbers in here. Negative pi over 2, and 3 pi over 2. Negative pi over 2, the negative sign of negative pi over 2 is going to be positive. The negative sign of pi over 2 is going to be negative. And the negative sign of 3 pi over 2 is going to be positive. So I am transitioning between concave up, concave down, and concave up again. Okay. I think that's weird, but we're rolling with this. Okay. So we have found f prime of x and f double prime of x. We have found the critical points. We have found the inflection points. We have evaluated f at the critical point, and now we need to evaluate at the end point of the interval. And then we need to identify local and global mins and maxes. So how do I evaluate at the end points? Any ideas? For how to evaluate at endpoints? What is the reason that I'm doing this? What is the reason I'm evaluating at the endpoints? Why do I care? Yes, I'm checking for the global mins and maxes. How do I compare? I would need to know what the coordinate points are, right? I would need an x value and a y value at the endpoints. what function am I going to put my x values into? F, F prime, or F double prime? The original, exactly. So I'm going to take f of 0, which is going to be equal to 0 plus sine 0, and f of 2 pi, which is going to be equal to 2 pi plus sine of 2 pi. This is going to be equal to 0. This is going to be equal to 2 pi plus 0 to 2 pi. So I'm going to end up with these 2 points, 0, comma 0, and 2 pi, comma 2 pi. Okay. So now I get to graph this. And I'm hoping that this will all make a lot more sense once I do. Right now, I'm not really sure what this looks like. Yes, so our critical point is, we've evaluated it. We know that that point is a point that exists. If I plug pi into my original equation, I'm going to end up with pi, right? So I'm going to put all 3 of these points onto this graph. So here is 0, here is going to be pi, and I need it fixed still. Again. Here's pi, and here's going to be 2 pi. And I'm going to extend this up. And this is going to be pi, and this is going to be 2 pi. So I have these points, right? 0, 0. I have 2 pi, 2 pi, and I have pi, pi. Okay. Next, I am going to mark out exactly where I am going to be concave up and concave down. Between 0 and pi, what do you think I'm going to be? So between 0 and pi, yes, that is this here. I'm going to be concave down. And now between pi and 2 pi, what do you think I'm going to be? Concave up. Given by that right there. So between 0 and pi, I'm concave down. Between pi and 2 pi, I'm concave up. So I'm just going to kind of sketch it out looking something like this. So I'm not like connecting them right now, I'm just connecting it up. And I know that I have a critical point that is neither a min nor a max here, so it's just going to be a flat line essentially. It's going to look something like that. Right there. And now I'm going to put it all together. And I'm going to draw it like this. Where it's flat, and then, okay. Okay. Yep. Exactly. Do I have any local maxes or mins? Nope. I don't have any. All right. So that is the graph of x plus sine x between 0 and 2 pi. And we just built that by checking all of these different things. Do we have any questions about this? Do you have any quick questions about 4.4 and marginal profit, cost, and revenue? Unfortunately, I have another session starting in just a couple of minutes, but if we have something quick that we'd like to go over, then we can do that. Okay. Awesome. Well, thank you all for putting up with the time swap on such a short notice. I'm so sorry about that. And I hope this was helpful. Thank you all for coming, and I hope you have a great rest of your day.